Hello and welcome to the fourth video tutorial for Intro to Dragon. In this video, we will be looking at a Dragon input deck for a can-do bundle, as well as looking at some of the results to find the K-effective and K-infinite. This is the data that was used when creating this representation of the can-do bundle. I will not go into too much detail about each section of this input deck, but will instead point out differences between this more advanced geometry and the single fuel pin that was created in the last video. One difference in this input deck is a few of the files being declared in the PS format. These files are in the PostScript format and will hold images of the geometry we will create with the PSP module. The modules used in this input deck are mostly the same as the ones used in the last example. The only differences are the PSP module and the CPO module. The info module is used in this input deck to calculate the weight composition of not only the coolant water, but also the moderator water and the weight composition of the UO2 fuel. All of these calculations use the IAEA library. A difference when calculating the composition of fuel versus the heavy water is instead of using temperature and pressure, the enrichment of the fuel must be stated. For this example, we are using 0.711 weight percent enrichment. Next, when we are declaring mixtures in the lib module, we are going to have 7 different mixtures. These mixtures are for the coolant, the moderator, the pressure tube material, the helium used in the annulus gap, the cylindria tube material, the fuel composition, and finally the fuel cladding. If you want to know what isotopes are part of these mixtures, please check out the IAEA material ID list. In the Geo module, we are using a carcel again, this time with 8 cylinders contained within the cell. Most of this is the same as the single fuel pin, but with more separate parts. The split R keyword splits the regions radially. Next, the cluster keyword is used to declare a pin subgeometry. The names rod 1, 2, 3, and 4 are the names of the pins. Next, we specify the pins have a tube-type subgeometry and that they have 2 subregions, one for the fuel material and the other for the fuel cladding. Next, the N-pin keyword is used to declare how many pins there are in each sub-tube geometry. R-pin is the radius of an imaginary cylinder where the pins sit around the circumference of this cylinder. A-pin is how much these pins are rotated around this imaginary cylinder. The radius and split R keywords are used in the same way here as they are in the carcel geometry. Now we are going to use the PSP module to create a picture of the geometry. To call this module, we are going to have to save the data in the PostScript format files we had declared earlier. And we pass the module the data from the Geo module. Next, we declare what type of image we want. In this example, we are going to call the module twice, saving the data in 2 different files. The type of image we are going to create will display the location of the different mixtures, and the other showing the different regions. After running this input deck, we are going to look at some of the output files. To open the .ps, you can use a PDF editing software. I am going to use the program called PDF24 Creator. Here we can see all of the different mixtures based on the color legend located at the top of the image. Next, we are going to look at the main output file of this run. The main output file is named after the input file but has a plus sign attached to it. By scrolling through this file, you can see the outputs of all the modules that have the edit level higher than 0. By looking through the output of the FLU, you will be able to see the results of the iterations that are used to calculate the K until it reaches a tolerable error. At the bottom of the outputs, it will show you the K effective and K infinite.